So welcome back, everybody, and to a new session. So what we are going to cover today is the new topic. So in the setup of a variational Monte Carlo code, one part which becomes essential is the optimization part. And I'm going to go through some basic steps in the optimization and why this is important. The other thing which we will do today is actually review some parts from last week, which are important for us when it comes to programming. So these are things which I gave to you guys as a kind of mini homework to actually look up these equations. So I'm going to quickly review the end parts of the slides from last week, which deals with a technicality. And I'm going to try to explain to you where this technicality enters and why we should pay attention to it, and how we can actually forget about this when we are going to deal with more complicated trial wave functions. But there are some technicalities which are worth looking at when we are writing our own program for a more complicated wave function than the one we have in the beginning. Then, as you see on the plans for this week, the optimization part is going to be important for us. And the reason why the optimization part is going to be important is that we can obviously, in a very brute force way, calculate for different variational parameters. And for every variational parameter, we can run, let's say, what is a typical calculation is between 10 million to 1 billion Monte Carlo cycles to get a good statistics. So if you have 100 variational parameters, you can then do the mathematics and figure out that you are going to waste a lot of CPU cycles away from the minimum. So what we want then is to use optimization techniques with few Monte Carlo cycles to find the best possible parameters, which hopefully are close to the variational minimum. When you then have these best possible parameters, that is when you start the big Monte Carlo machinery, where you sample millions and millions of configurations. So the optimization part is an essential element of us making the code more efficient, where we sample around the variational minimum instead of placing ourselves randomly in the space of variational parameters and then just in a brute force sample a whole set of them with a full-fledged Monte Carlo simulation. So if you do 100 parameter and you run 1 billion cycles for each, then you would have 10 to 10 samplings in total. And you can actually get away with perhaps only 1 billion if you then do a smart optimization first. So this is really time saving for us. So what I'm going to do now is just to quickly go through the things from last week. And then after that, I will jump into the whiteboard and we are going to look at the optimization part, and we're going to step ourselves from a simple parameter, which is the case in project 1, to many parameters, and how we are going to implement the optimization itself, and what is the best algorithm for doing the optimization with the number of variational parameters which we have here. In our case, the simplest gradient descent is often the method we end up implementing. But we are going to discuss methods like gradient descent, stochastic gradient descent, conjugate methods. We have the steepest descent, and then we have the family of quasi-Newton methods, which are the methods which will be more interesting for us in project number 1. For those of you who would like to work with an implementation of a neural network to this problem as part 2, then a method like stochastic gradient descent, where you have tons of parameters when you're training a network, that becomes more interesting. But for this project here, a standard gradient descent or quasi-Newton method, which we will discuss next week, are the methods which are the most reliable ones and also the easiest to implement, and those which save most CPU cycles for us. So there's always this compromise when we are setting up an optimization code, what is the type of problem we are looking at? Are we interested in having a general set of methods which we can apply to different cases? Or do we just want to specialize to the specific case which we have? So that's the kind of path I will guide you through now. And then we will also discuss more advanced methods. But for project number one, the simpler methods like quasi-Newton methods are the most relevant ones. Yeah.
This might be a redundant question, but is there a method to sort of automatize how you pick the methods?
Could you say it again?
Is there a method of automatizing which method you pick for the problem so that you achieve it supported to have assets?
I am not familiar with that, so I don't have a good answer to it. So you would like to optimize which method to optimize with, right? I think you have to more use a kind of experience and see how many parameters you have, because like now we have just one parameter. And if you're dealing with many parameters, you reach quickly a point where like a stochastic gradient descent becomes the only possible method. Okay, so let me quickly remind you of a thing which I gave as a kind of reading assignment. So this is a background technicality, and this is from last week. So I'm just going to scroll down here after all these technicalities with the Fokker-Planck equation. And I wanted to point out some of these technicalities which deal with the way we perform the calculation of the correlated part of the wave function. So the technicality which you see here is very much connected with us looking at an interacting system. And you see now that we have a correlated part of the wave function, and this is actually the complicated animal. So often then, this correlated part of the wave function is rewritten in terms of a series of exponentials. This is the most common form of what we call the Jastrow factor, or just the correlated part. So this is us baking in information about the Hamiltonian, so that we, for instance, cancel a divergence in the two-body kinetic energy. That cancels a divergence in the two-body interaction. Now, if you're dealing with a field like nuclear physics, or you're dealing with material science and you're fitting forces, you will often end up with a free-body force, which is an effective force. And then you will have two free indices. Instead of I and K, you will have I, J, K, and so on. So you can make more and more complicated correlated part of the wave function, yeah?
For a Gaussian distribution, would this just be the non-diagonal part of
the... Yeah, exactly. So if you think in terms of a standard many-body problem, this is actually what gives rise in a diagonalization type of problem. This gives rise to the non-diagonal matrix elements. So this is, if you think now of the project, we have said now that in the beginning, we are going to look at just a product of single particle wave functions. So that part is pretty simple to calculate the kinetic energies of. So everything you see here is tailored towards the calculation of the quantum force and the kinetic energy. That is the computational bottleneck in these variational Monte Carlo calculations. So when you are setting up a variational Monte Carlo code, the potential itself does not change the wave function, which means that when you calculate the local energy, if you have a potential acting on the wave function, it doesn't do anything, and then you divide with the wave function, and then you're just left with a contribution from the potential energy. However, when you calculate the kinetic energy, you're going to need the first derivative and the second derivative. And this is the computational bottleneck when you include the correlation part. So we are not focusing on that now, but it becomes important at the end of the project when we are going to bake in the interaction. Because now when we are building up the code and testing the mathematical elements, we are putting less emphasis on this. So this is something you can postpone, or if you're collaborating with people, you can say that one of us is going to look at that specific part. because you will need it. But this is perhaps not the most exciting thing, but it's an important technicality. And it becomes important when you have many particles. Okay, so just view this as a technicality. And the reason why I listed here that there are some elements which we need to think of is some tricks you can use. So one thing is obviously that when you calculate this correlated path, there are no self-interactions. And this is why we can split the sum into a sum up to k minus 1 and from k plus 1. So self-interactions are not included in the Hamiltonian. And the typical form of the wave function, which is a form which then allows us, if you look at what you have here, this, if you think of that, you can write this as the derivative of the logarithm of the wave function. So now I'm setting up this in a brute force way, but when you're going to compute it, then you are going to rewrite this as the derivative of the log. And then if the wave function, the trial wave function, has a series of exponentials, that simplifies the logarithm. So many of these trial wave functions, they contain information about the wave function. And often what you look at, if you look at a basic quantum mechanical problem, and you take the interaction, you can, when you take the limit when r goes to infinity and the distance goes to 0, you have some constraints on the wave function from the Hamiltonian, which you can plug in the ansatz for the wave function. So like we saw last week, no, I think it was a week before, when you have a type of Coulomb type problem, there is a divergence in the kinetic energy, which has to cancel the divergence in the potential energy. And that enforces an exponential part in the solution. And if you remember back to the solution of the hydrogen atom, you have an e to the minus r multiplied with polynomials, which are called Laguerre polynomials. If you take a two-body problem, there will be a similar exponential part, which is a minimal requirement in the wave function. So many of these trial wave functions are often expressed as exponentials. Or if you don't have that, you can then express it in the way as you see here in this second equation. And that often facilitates the way you calculate these derivatives. So just keep in mind, these are small technicalities which are worth thinking of. Now, for the problem which we have, the kind of ratio which we also need to think of is the ratio between the new wave function and the old one in a metropolis test. So we need to look at that one. And then when we calculate the quantum force, we need this quantity. And when we calculate the quantum force, you will see now that there will actually be a gradient of this term and the gradient of the correlation part. So we need to calculate these terms. And then when you calculate the kinetic energy, if you just scroll down here, there will be obviously a gradient which is the same as you have calculated now. Not a gradient, a second derivative. And then you have a second derivative of this quantity. But then you have a gradient times a gradient. So everything here, when you calculate the kinetic energy, is a scalar. And here we have two vectors multiplied with each other. So these are technicalities which we need to consider when we are setting up the full code. So what you have here is a typical type of the correlated wave function, which we then can rewrite as these two products. And then it's convenient, since this Rij is just a relative distance between two particles in either 3, 2, or 1 dimension. Then it can be actually useful to set up a matrix for the positions, for the interparticle positions. And then just keep in mind that we typically move one particle at a time. And that means that only one of these rows or columns will change. So when you're calculating, it can be convenient to set up the interparticle distance like that. And then the difficult part, which you will see, is going to be this term here. And the one which we have to think of as well is the products of these two gradients. Now, in our case, in project number 1, we are going to have an expression for the second derivative and the first derivative of the trial wave function, which we can implement from an analytical calculation. So this is something to think of. So when we are developing the program, we have to strike a balance between, one, if the expression is simple enough, it can actually be convenient to calculate analytically the gradients and the second derivatives, and then simply code that one. The examples I have in the lecture notes for this 2 electron case is an example of that. Now, if you want to follow up project 1 with the implementation of a neural network, then it's going to be more interesting to use automatic derivation to calculate the second and first derivatives. Because then you're going to have so many parameters, and the trial wave function is going to be a neural network, which means that you don't have a nice analytical expression for the trial wave function. So these are considerations, again, to think of. So for project 1, we are going to have a nice analytical expression, and then many of these considerations here about the numerical calculation can be left to just us programming it or just hard coding the derivatives of the trial wave function. So in the examples, as I said, for this 2 electron case, I have hard coded the expressions for the derivatives. So you need, in a way, when you are looking at the different tasks, you need to make a decision how you want to implement it. So in the things here, I'm not going to go through this in great detail because this is not a too exciting topic to calculate derivatives. I hope you don't get offended if I don't go through the calculation of derivatives. But what you need when you're setting up things here, if we scroll down a little bit. So I just included all these technicalities for the sake of completeness. One of the things you need to take into account is that this function g is a function of the relative distance. But we are often calculating that with respect to a single particle state or single particle position. And that means when you calculate that with respect to a single particle position using the chain rule, gives you a slightly more complicated thing here. So what you're doing now as a product of single particle wave functions is pretty straightforward to calculate. But when you come to this piece here, you need to be a little bit more careful. And I'm just listing these expressions. So when you go then down and look at, so down here, there is a typical general expression which you can code when you have a function. If you now have a correlated part, which is written in terms of these exponentials, this will be the more general expression you would have for the second derivative with respect to one of the variables. So the kind of homework which I gave you last time was simply to convince yourself that this is an expression which makes sense. So this is something which we would have to encode if we want to make the code slightly more general. And then you see that the only thing you need then is to specify this function f, which represents the way you set up the correlated part of the wave function. Then we need this expression here, but we need also the first derivative, which is this part here for the quantum force. And then when you have this piece, you need to take the gradient here. When you're calculating the kinetic energy, there is a cross term, and that cross term is the one which we have to plug in here. So we have this gradient multiplied with that gradient. Does that sound okay? Any questions to this exciting technicalities? Okay, so let's if you have no questions about it, let's now move over to the topic today, which is actually about the optimization. And we are going to look at different methods, and I'm going to switch over to the whiteboard now, if it's okay. And I want to step you through the basic ingredients which enter the calculation of these derivatives. And if you scroll down here, we are going now to take a kind of top-down approach to it. I'm going also to show you how you can implement it numerically. Next week, we are going to look at not Newton's method, because that's something we will cover today, but then we will discuss the conjugate gradient method, which is a very popular method, which you're not going to use anyway. So, but it's useful to have seen it. And then we are going to discuss quasi-Newton methods, which are very useful for what we will do in project 1. For project 2, again, if you're dealing with neural networks, it will be more convenient to actually think of using stochastic gradient descent, which is the standard method for an optimization of a multivariable function. Okay, so let's switch to the whiteboard and go through the basic elements which we need to set up. So what we are calculating is the following. So let's just put a header here. This is the optimization part. And I want to tell you why we are doing this optimization. I mentioned this in the beginning, but I'm going to repeat the parts of it. So formally, we are calculating an expectation value, E, and we are calculating an expectation value of the local energy, which is a function of a set of variational parameters. So alpha could be one parameter, like we are doing in project 1, or you could have many parameters. So I'm just writing this as a vector. And that's given by a multidimensional integral, where we now have this probability, which is a function of these vectors alpha and r, multiplied with a quantity which is the local energy, which is a function of both alpha and r. And let me quickly remind you of what we are setting up. So this is given by the trial wave function, psi t trial, as a function of the positions of the particles which we have, divided by the norm. And then I'm getting a little bit sloppy here. Okay, well, let's write it out like this. So that's this quantity. And then just to quickly remind you of the last quantity which we have here. This is 1 divided by psi of t of r of alpha of h acting on psi of t of r of alpha. So if we have one parameter, what we typically end up with, so if alpha now is just equal to one alpha parameter, alpha, what you would typically end up with is something like this. So we have a E, an expectation value, and this function could look something like this. And here we would have the optimal parameter, which I'm going to use a hat on top of it. So this is alpha opt. And typically what we would do is to calculate this for many, many different points. And we may not hit the minimum. And then we're going to make an interpolation. And that interpolation is a function which we would use then to find the minimum. So we can parameterize in terms of the points we have, we can parameterize the polynomial, and then we simply take the derivative of that polynomial, and hopefully we find this exact point here. So each one of these could be something like, each one of these could be, let's say, 10 of MC cycle, 10 to the power of 8 MC cycles. We would do it here, 10 to the 8, etc., etc. So if I have 10 points here, that means that I get to 1 billion Monte Carlo cycles. So what I would like to do now is actually to reduce this kind of brute force approach to us making a calculation where we pick a specific value, and then we just use, let's say, 10 to the 5 to 10 to the 6 calculations. And then we calculate the gradients. And with the gradients, we are then going to find this point here. We find the minimum where the gradient delta E with respect to alpha, this expectation value of the energy, is equal to 0. So we are going to use a gradient descent method or some gradient method to find that point with as few cycles as possible. This is a basic strategy which is used in all these Monte Carlo simulations. So you can obviously, like in the examples which I showed you, I calculated these points here with 10 to the 6th to 10 to the 7th Monte Carlo cycles, and that takes a lot of time. And then at the end, I get a curve, and then you interpolate and find the optimal parameters. This is a very inefficient strategy. So in all the Monte Carlo codes, what you will find then is that there will be a drive towards an optimal set of values. And when you reach this point here, where you have a gradient which is as close to 0 or as close to what you have defined as 0, then you can start the big Monte Carlo machinery. And since you can parallelize easily these codes, it's very easy to run many calculations in parallel to perform this. So you see the basic overarching strategy here. Now, one thing which disappoints many people with what comes now is that all these methods are actually based on us performing a Taylor expansion around the minimum. And then we keep only terms to the second derivative. If we do that, that gives us a famous method in optimization theory, which is called Newton-Raphson's method. And that's the starting point for all optimization problems. So if you're taking a course in optimization theory or convex optimization theory, then you will see that this is essentially what you end up with. So all these other methods like conjugate gradient, steepest descent, etc., they are just iterations around this Taylor expansion. Yeah.
Let's just say I understood it. So we begin by doing one like Monte Carlo cycle to map out the space.
Yeah.
And in this space we find sort of the minimum iterations.
Yeah.
And then we do the larger.
Exactly. So you would typically, often, you have a kind of idea of where the minimal parameters are, but you could start randomly in parameter space. And then depending on your algorithm, if you have also, in most cases, we are dealing with convex problems. An energy optimization problem is mathematically, in most cases, a convex optimization problem. We are looking after the energy minimum. And there are actually theorems on the type of Hamiltonians which you end up with dealing with, which simply tell you that these will lead to a convex optimization problem. So the problem itself is a convex, you're actually having a convex function in a space of many variables. Okay? So this is a kind of overarching philosophy of what we are going to end up with. So let's just now simplify life a little bit. And I'm just going to introduce a series of shorthands here. So I'm going to just define some, I'm going to rewrite this expectation value of the local energy with respect to these parameters alpha. I'm simply going to label this as an E of alpha. Okay, this is just for simplicity. Then we are going to perform a Taylor expansion. I'm going to calculate derivatives. So I will need the gradient of E of alpha. And I'm going to label this as just a G in the notation here of alpha. And I'm going to be a little bit more on the simplification side today. So I'm simply going to replace alpha with just a variable alpha. And it will be clear from the context whether this is a scalar or a vector, okay? So I'm going to just have then a function g, so this becomes a function g of alpha. Then I'm going to perform a Taylor expansion. So I'm going to Taylor expand this energy, E of alpha, around the optimal value. Which I label as alpha hat. So that's going to give me a quantity which I will now label as a alpha minus. So this is I'm expanding around the latest iteration. So this is alpha of n. So this is after I've done this many times, iteration n. I'm going to solve this problem in an iterative way. And I'm going to label this as a quantity b of n. So that means that I will also have a g general alpha, which is actually a g of alpha n. And I'm just going to use this shorthand here, g of n. Okay, these are just shorthands which I'm introducing. Then, since I'm going to Taylor expand, I will also need second derivatives of the energy. So I'm going to have a second derivative with respect to these parameters of the energy. And this will now be given by the second derivative of these parameters alpha, calculated at a value alpha of n. Now this is, if I have many parameters, this is a Jacobian matrix. But I'm going to label this as an A of n. Okay? So these are just namings which I'm setting up. And if I now do a expansion, so it means that what I'm doing now, I'm Taylor expanding E of alpha around that point. So this is going to be given by E of alpha n. And I'm going to introduce a new one. So E n is the same as E of alpha n. So this is my optimal value. And this is going to contain a plus. And I will obviously have the parameters I'm expanding around. So I will have a B of n. And just a moment, I'm just gonna, since these can be vectors, they are not necessarily scalars. I will have a vector, which is the gradient. I transpose it and I multiply with this B of n. So let me, if you just have a scalar, that would be the derivative G of n multiplied with alpha hat minus alpha n. But now, since I can have more than one parameter, these are vectors, and the final energy is a scalar, so I have to take the inner product. So G is the first derivative, and alpha minus alpha n is simply the step difference which we have. And then I have the second derivative. I get a plus half of b n transpose. And then I have to multiply with the second derivative, a of n, times the vector b of n. And then I have higher order terms, O of this b of n to the power of 3. So let's just look at this in case it's a scalar and in case we have two parameters. So suppose you have two parameters. So with two variational parameters, with alpha is equal to alpha 0 and alpha 1, then the gradient which we need, this G of n, is a derivative with both respect to alpha 0 and alpha 1. The second derivative is then given by the Jacobian matrix. So that would simply be of d of E of d alpha 0 squared. And this is evaluated at alpha equal to alpha n. I have a d second derivative, and then I get the cross terms, alpha 0, d of alpha 1. And again, this is evaluated at these specific values. Then I have the second derivative here. I have d alpha 1, d alpha 0, again evaluated at this term. And finally, I have a d of e of d alpha 1 evaluated. And just keep in mind now that I'm a little bit sloppy with the notation. So alpha is a vector now containing two elements, evaluated at iteration n. Now, what you're going to see is that this quantity is going to be an ugly beast to evaluate. So this is common. Yeah, you have a question?
It's symmetric, right?
Yeah, it's symmetric. This can be symmetric. It can normally it's symmetric. Exactly. This is called in the literature. This is called the Hessian matrix, and this is a symmetric matrix. That's correct. But still, when you are now going to see the expressions for the gradient, you are not going to be willing to calculate the second derivative, because the second derivative is going to involve 7 integrals. The first derivative is going to involve 3 integrals. And if you have a 10 particles in 3 dimensions, each of these integrals will be 30-dimensional. Okay? So this really begs for ways to find an expression for the second derivative, which can be used efficiently in computations. Okay? So I'm trying to give you the kind of overarching elements here, which we need to plug into the coding. So the gradient contains now, for this case, just 2 variables. If we are just having a single variable, just an alpha 0, then we don't need to have these transposed quantities. Then the expressions are much simpler. What we are going to do then is that we are going to assume that high order terms can be neglected. Then this function which we are looking at, this e of alpha hat, is going to be given by this e of alpha n, which we also call for e of n. This is a notation which we're going to use. This is just a constant. We have calculated that from the previous iteration. And then we have an expression which goes like plus, and then we have g of n transposed, multiplied with this b of n, and then plus 1/2. And then I have my b of n transposed times a of n times b of n. This function which you see here, that looks like it's of the form, which you may have seen in linear algebra courses. So this is normally what we call a quadratic form. And x is now a vector. It can be a scalar. It's given by a constant, c, plus some vector x multiplied with a gradient, where g is the derivative of this function f of x, plus 1/2 x of t times a matrix A times x. Now g here doesn't need to be the gradient. It doesn't, because you could have a function which is much simpler than the one you see here, but this is a general type of problem which we end up with. And when you now calculate the derivative of this one, df dx, and we put that one to 0, then what we have is that we get a times x plus g. So now I'm calculating the derivatives of a function which includes vectors and matrices. This is a famous problem in linear algebra, which you probably have seen many times. The brute force way of solving this, if the matrix can be inverted, is just simply by calculating these quantities here. And what you assume then is that g is known, a is known, and x is the unknown quantity. This is essentially the type of problem which we end up with. So if you then think of a simple example of what you have here, so let's just do that. And we are going to see this example being used next week in the code examples. So let's just take a simple example before we take a break. So a simple example could be us now picking a function of two variables, x1 and x2. So we have a vector x, which is just x1, x2. But suppose we have a function which goes like this. This is one way of writing it. And I think you may have seen something similar when you took a course on linear algebra. And then I have minus 5 times x1 minus 3 times x2. So this is just a function which I cooked up on the fly. Now I can rewrite this now in terms of this matrix vector relations which we had. So I can rewrite this as, so this quantity here, as 1/2, and then I have this vector x transposed, which contains x1 and x2. It multiplies with a matrix A. So this is a matrix A, which has now 2, 1, 1, and 20. It multiplies again with a vector x1, x2. And then it has a new vector where I have the transpose of that vector. It's 5 and 3 multiplied with x1, x2. And I'm going to just label this as a vector b of t. So if you multiply out, you see now typically the first one, now the last one gives us minus 5 times x1, minus 3 times x2, when I multiply everything out. So remember now that I have a vector transpose times a matrix times a vector, that becomes a scalar, or just an expression, which in our case turns out as an expression in terms of x1 and x2 here. So this form here is just another way of rewriting what we have here. Then I can calculate the derivative of that quantity. And if I calculate the derivative of that quantity, if I now require df, dx, I want to find the optimal values. Then if I do that, what I can find is that x is given now by a minus 1 times this vector b. Alternatively, I can actually just set up df dx1 equal to 0. And that gives me 2 times x1 plus x2 minus 5. And I hope you don't get offended if I say that this is a type of equations which are pretty easy to solve. And they are. So we've seen this many times before. We have two variables, two equations. We know how to solve that. And then we find these an expression for x1 and x2. So what you have here is one way of solving the problem, because then you find x1, x2 immediately. Or alternatively, you can just do this. Or you can start iterating. So if you go back to the equations which you had, oh, sorry, let me just wait a little bit. So the next approach now is actually to start with a guess, which I call x0. And this is now going to be a vector which I can just set up. And this vector could just be a random vector which I pick, let's say minus 3 and 1. There are several interesting mathematical properties here, which I'm going to state without proof. One, this matrix A, which you have, is a positive definite matrix. What does it mean if a matrix is positive definite? Does anyone remember that? Yes. So this matrix which you see here has all eigenvalues larger than 0. Now, in linear algebra, and when you look at this from an iterative point of view, it means that you can start with any random starting point, and it will always converge to the exact solution after a given number of iterations. if you have a matrix A of this type here, which is positive definite. That's a very important aspect of it. And in our case, we are going to deal with matrices, the second derivative of the Hamiltonian, which are going to be positive quantities. So our Hamiltonian matrix, or our Hessian matrix, the second derivative, is going to be a matrix which is positive definite. And we know that if we have a convex optimization problem, we know that the second derivative is positive, right? So that is, but there is more bonuses than that. So we have a convex optimization problem here. But the other thing, if the matrix is positive definite, it will always converge to the exact solution, irrespective of starting point. If you start far away from the minimum, it will take more time to get there. That's the same with the optimization of the energy. So after the break, we are going to go back to the expression which we had here, this one. And from this expression, when we take the derivative of this one with respect to alpha, we are going to find Newton's method. And then we are going to find the recipe which we are going to implement. So this was a kind of more the overarching picture of what we want to set up. And I know that people get a little bit disappointed when they say that, hey, all the fuss around this optimization is actually us assuming that we can truncate this Taylor expansion at the level of the second derivative around the optimal value. There's no guarantee, actually, when you run these calculations, that this term here is smaller than that term. Okay. Let's take a small break, eh? Right? And if you have questions, I mean, feel free to come with them. So what we are going to do now is simply to calculate the gradient of this expression here. And we want to drive that gradient to zero. So essentially what we are doing now is to take an expression of this form, which looks very much like this. And the simple example, which we looked at before the break, was this example here. And that is a case which we can calculate either by simply inverting the matrix, or by simply solving this equation here, or we could solve it iteratively. And if we do it iteratively, if we now go back to what we had, so we have this equation here, this is the equation which we will solve iteratively. So I'm going now to go back and we are going to calculate the gradient. So what we need is the following. So we need the gradient of this energy, E, with respect to this parameter alpha hat. And now I'm going simply to rewrite this alpha in terms of iteration, because this will be solved iteratively, of alpha n plus 1. So the gradient then, we want to drive that to 0. D of E of alpha n plus 1, we want that to be 0. And if we take the expression then, what this gives us is simply that we have a term. If we now look back at the expression which we started with, this is going to give us, when we put it to 0, that will give us an expression which will contain G of n multiplied, because we take the derivative now, and then we will have a plus, and then we are going to get this matrix A of n multiplied with this vector B, which is the unknown, the quantity which we put up in the beginning. So this is going to be given by B of n, and this is the quantity. B of n is a quantity which is given as alpha n plus 1 minus alpha n. And G of n is just the gradient of the energy which we have calculated at the value alpha of n. So let me just remind you that G of n is now the derivative of the expectation value of the energy at alpha of n. So we take the first derivative, and if you look at this expression here, that means simply when we take this to be equal to 0, what we get then is a pretty simple expression which runs like this quantity alpha of n plus 1 minus alpha of n, which is now equal to minus, and then I multiply with the inverse of this matrix, an minus 1, multiplied with the gradient g of n. If I then shift over what I know, I have alpha of n equal to alpha of n minus a of n minus 1 times g of n. This is the final expression. And this has a famous name in the mathematics literature or numerical mathematics. Does anyone remember what we call this expression here, or this iterative expression? Say it again. Newton's method. You have probably seen this in the disguise of xn plus 1 equal to xn minus the function value at xn divided by the derivative of xn, right? This is the formula which you probably have seen in normal textbooks for just one variable, x. So this is just nothing but Newton-Raphson's method. Raphson's method for finding the root of a function. In our case, the roots which we want are the roots of the gradient. And since we want the roots of the gradients, that means that the quantity which we have here is the second derivative. In the standard Newton method, which you see in most textbooks, you're just looking at the root of this function f, and then you need the first derivative. But we actually having the roots of the gradient. And that means that we end up with a second derivative here. So this is just nothing but Newton's method, which is solved iteratively. And if then the alpha n plus 1 minus alpha n, if that is smaller than a given value, so you would solve this iteratively. So solve iteratively. Till, if we take these as vectors, alpha of n plus 1 minus alpha of n, and this is the norm 2, is smaller or equal to a predefined quantity epsilon. If that is the case, you would stop the convergence. But in many cases, this is a very time-consuming thing, and you just stop the iteration after a given number, the iterative process after a given number of iterations. Now, what you see here is that you have a second derivative. So the quantity an is a second derivative, and this can be a large matrix, and we have to invert that matrix for every iteration. And this is often something which we want to avoid. And what is common then is actually to replace that one with a constant. So it's common to replace this a of n with a constant which can vary from iteration to iteration of gamma of n. So for those of you who have taken a course in machine learning, you recognize this quantity as what is normally called the learning rate in machine learning. And this is one of these huge topics in machine learning, actually. At the heart of every machine learning method, there is an optimization process. And that optimization is perhaps often the most tricky part in all of machine learning, because you are trying to optimize a function, which in our case is the cost function, which you define in order as a gauge of the quality of the model. And that cost function can be a function which depends on millions of parameters if you're dealing with deep learning methods. And that optimization part, as I normally say half jokingly, is actually one of these parts where you can get many new friends. So I'm not saying that you don't have friends, but this is a set of friends which will cite you. Because the optimization part, there's a famous algorithm for tuning this gamma of n based on information on the gradients, which is called ADAM. Some of you may have met that one. It's an adaptive gradient with momentum. That paper has more than 150,000 citations since 2014. A good physics paper, a very good physics paper, has 100 citations something. So this, we are talking about many orders of magnitude more citations. So when you understand in a field like deep learning and machine learning, to have something where you can efficiently optimize a multi-dimensional surface and find the minimum of that one is something which is simply essential. So you could say now that the mathematics which we have dealt with is actually just a Taylor expansion, which is truncated at the level of the second derivative. The problem we however face, as you will see pretty soon now, is that this second derivative is something we want to avoid to calculate. And what you end up with typically then are methods where you can estimate this gamma of n in some way or the other one in a reliable way. And if we called the basic method for Newton-Raphson's, you can find methods where we try to find an estimate of this second derivative, which are called quasi-Newton methods. And one of these are methods which you will see implemented in a library like SciPy, Scientific Python. And we are going to discuss one of these methods next week. But today we will stay mainly with the basics of the Newton-Raphson methods, but where we now are going to replace this second derivative with a parameter. And this parameter gamma of n is something which we can set to a constant and just keep it as a constant. So if we make it small, then you will barely move when you multiply with the gradients towards the minimum. If you make it too large, you will jump away from the minimum. So this is a parameter which needs to be fine-tuned. But let's see if we can gain some information without doing much mathematics. So let's now look at this parameter gamma. So what we can end up with then is the following recipe. So what we need now is to pose the questions: how do we find the optimal parameter gamma without calculating the second derivative and then inverting that matrix? So let's make an expansion now. Let's expand this expression, the energy for the energy around an alpha of n minus gamma of n of g of n. So let's suppose, because this is now back to Newton's equation, right? We found that alpha of n plus 1 is equal to alpha of n minus gamma of n multiplied with g of n, right? So this is nothing but Newton's method, where we have replaced the ugly second derivative with just a constant. So we just expand the energy around that, and then we can now obtain an expression in terms of this gamma. So we will get an energy calculated at alpha of n. We get minus gamma of n, but now we have a g of n transpose times g of n. And then we have the final term, and we status, if we now just set up a Taylor expansion, we get plus 1/2 gamma n squared, and then we have a g of n transpose times this matrix A of n, which is the second derivative, times g of n, and then we have higher order terms of this quantity alpha of n minus gamma of n of the g of n to the power of 3. And then again, we assume that we can neglect higher order terms. So we just neglect these ones. And then we are back to a simple expression. So what we get then is that this energy of alpha of n plus 1, which we are simply going to calculate or to replace with an alpha of n plus 1. This is given by this constant E of n minus gamma of n, g of n transpose times g of n, plus 1/2 of gamma of n squared. And then I have a gn of t, and then a of n of g of n. Now, this one depends only on the previous values on gamma of n minus 1. So what I'm going to do now is simply to calculate the derivative of dE of d of gamma of n. And I want that one to be 0 to find the optimal gamma. So if I take that derivative, what we find then, when we do that, I find then that gamma of n is equal to g of n transposed times g of n. And these are all scalar quantities. And I have g of n of t times a of n of g of n. Now, next week, we are actually going to see that this is nothing but the standard method, which is called the steepest descent. So this is in the literature, and this is what we will derive next week. This gives us the steepest descent algorithm. Now, what you see here is that you still need to evaluate this quantity here. So in a way, we haven't avoided any problem if we want to insist on the steepest descent. And that's why we are not going to use the steepest descent in these calculations, because that means we have to calculate the second derivative of the energy. And we don't want to do that. And as I said, this involves 7 Monte Carlo integrals to be performed. So this is a quantity we want to, in a way, not do. However, let's say now, as an example. So suppose, as an example now, that these gradients are the eigenvectors of this matrix A, just as an example. So suppose that the an times g of n is equal to lambda times g of n. This is something which becomes important when we are looking at the conjugate gradient method. So this is a technique. So these things are not irrelevant for what we will discuss next week, although we will not use these methods because they rely on us being able to calculate the second derivative. So if you do that, then we know that this gn of t, we assume that these are just normalized to 1. Then what we find is that this gamma of n is simply equal to 1 divided by lambda. So that gives us actually some insight about the parameters gamma of n in terms of the eigenvalues with problem which we have set up here. So then the step size, so if you think of gamma of n as a step size, has constraints which are given by the maximum and minimum eigenvalues. The step size has min and max values, has a min value, which is given by 1 divided by lambda max, and max value, which is given by 1 over lambda min. So if, and for some of you who have studied, let's say, convex optimization theory, you may have heard of something which is called the optimal ratio for this convergence process. And in that case, you have something which we normally call the condition number, which is the ratio between the maximum eigenvalue and the minimum eigenvalue. So if these eigenvalues are very different, what happens then is that this process will converge slowly because you have a big span eigenvalues. If they're concentrated, it normally converges rather quickly. What you can find in general, however, is a mathematical requirement, which we are not going to prove. So one can show. And these eigenvalues, which I'm setting up now, are the eigenvalues of the Hessian matrix. One can show that the optimal gamma value has to be smaller than 2 divided by lambda max. Anyway, this hinges on us being able to calculate the Hessian matrix or the second derivative. And as I said, we want to avoid that. And now you're going to see why we want to avoid it. So everything we've done now means that we are able to calculate this A of n. And you will see that with methods like steepest descent or conjugate gradient descent, etc., they rely on either that this matrix is a constant, it doesn't change by each iteration, or it's a matrix which is easy to calculate the inverse of and find the eigenvalues. If not, many of these methods, they actually require us being able to calculate this ratio. And if this ratio becomes difficult to calculate or not difficult to calculate but time consuming, we want to avoid that. So these are the kind of considerations which we have to think of. The problems which we have in project one leads to only one parameter. And in that case, we don't need to deal with all these worrisome things with calculating gradients and the second derivatives of a matrix, which of the energy. The expressions are going to be much, much simpler. So let's now see why we would like to avoid calculating the second derivative. And what we need to look at now are the expressions for the expectation value of the energy and the first derivative and the second derivative of that. So why do we want to avoid calculating this quantity here, A of n, which is now the second derivative of the energy at a given value alpha. And we call this E of n. So it means that since this energy is going to differ from every iteration, it means also that we have to recalculate the second derivative. So let's look at the expression for the first derivative. So d of E of n, which is the same as the derivative with respect to this parameter alpha. And the easiest way to set it up now is just to use the harmonic oscillator case which we have. So let's now use an example, and then we're going to generalize this. So this is a one-dimensional harmonic oscillator. And in our case, as we have in the project, this trial wave function, Ct of x and alpha, so we have only one parameter, is given by e to the minus 1/2 of alpha squared of x squared. So life here is much simpler, also because the function contained is a real function here. So we don't have an imaginary argument. This makes life much simpler. But let's now look at the expression which we want to calculate. So in our case, the expectation value of the energy, which I'm now writing in this more compact notation, is given by this integral d of x, and then I have e to the minus 1/2 of alpha squared x squared of h times e to the minus 1/2 alpha squared x squared, and divided by d of x, and then I end up simply with e to the minus alpha squared of x squared. Or if we wish to be a little bit more general, what we have now in one dimension is d of x, and then I'm just going to write this as an alpha of x, complex conjugate of h of c of alpha of x, divided by d of x, and then I have c alpha of x. So you see now that when we're going to take the derivatives, we can take the derivatives inside the integration sign without problems, because the integrand is not an integrand which involves, or the integration does not involve alpha. So what we have then, if we take the derivatives, so let's just do that. So we need now dE with respect to this parameter alpha. So it shouldn't be a surprise here. If we now just write this out, we get a factor of 2. I'm using the hermeticity of the problem which we have at hand. So I have a d of x. I'm going to get an h times psi alpha of x, but I'm also going to have a derivative d of psi alpha of x of d alpha of 1 divided by psi of alpha. And this is divided. So I'm just using the standard rules for taking derivatives. And this has a psi of alpha of x squared minus, and there is a new factor of 2 here, which is now given by d of x. And then I have my standard local energy here. So I'm going to have a psi of alpha of x of h psi of alpha of x divided by the denominator, one of the denominators, because I have to square the denominator. So I'm just going to write it like this. And this quantity is then multiplied with a new integral, which is just d of x. And then I have psi of alpha of x times, no, sorry, this is not, I did something wrong here. So this should be times psi of alpha of x. So this is multiplied with d psi of alpha of x of d of alpha, and divided by the other denominator, because I have to square the denominator. So what you see here is just simply the numerator multiplied with the derivative here. So this is the second term which I get when you now can use the standard rules for taking derivatives of numerators and denominators. So you have one term, and this is the first term here, which we recognize as simply the local energy. This is now the expectation value if we now look at this quantity which you have. So let's take first a look at this expression here, this one. And what I'm going to do now is to multiply with a wave function and divide with a wave function. So I multiply and with psi of alpha and divide by psi of alpha here. What I get then, if you take the second term, and let's just take a look at that one. If I take that one, what I have is a d of x, and then I have a psi of alpha of x multiplied with d phi of alpha of x, or d of alpha, divided by d of x of psi of alpha squared. And then I multiply simply with psi of alpha and divide with psi of alpha. And these functions are real functions, so we don't have any problems with just writing it like that. But you can then show that if you look at a function which is complex, you simply need to set up the right expression there. But this is something which we can rewrite now, because we are going to have a d of x, and then I have my psi of alpha of x, and I just rewrite it like this, squared, multiplied with the derivative of ln of psi of alpha of x respect to d of alpha divided with d of x multiply with psi of alpha of x squared. And this is nothing but a probability, the same probability which we described earlier, multiplied with d ln of psi of alpha of x divide the derivative with respect to d alpha of d of x. So this is the expectation value of this quantity here. Then, if we go back to the expressions which we have, you will see then
I have a question. I don't know, maybe I don't follow it. In the second step,
Yeah,
when you change the derivative inside the integral, like a
yeah,
logarithm, see
yeah,
alpha, see phi alpha is a complex, for example, denominator. It's possible to
yeah.
do this.
Oh, yeah, yeah. No, this. So what I'm doing now is I'm simply setting it up for the case of the harmonic oscillator, which is much simpler. And then I will leave it as a small exercise to you guys to actually do this for the general case. And there you simply have to use the hermeticity of the Hamiltonian. So this is something which so I said I'm specializing this to the harmonic oscillator case, which is a little bit simpler, but then you see the way the expressions come through. So if you look at the expression which you have here, this one is an expectation value. If we then go back, here we have the standard expectation value of the energy. And this one, by doing the same trick, can now be rewritten as a new expectation value. So I can rewrite everything in the following form of dE of d alpha, which then is equal to 2 times the expectation value of d of ln psi of alpha, of d psi, now d alpha, multiplied with the local energy, which depends on alpha. That is one expectation value, that's one integral we have to evaluate, minus 2 times the expectation value of psi or alpha of d alpha, multiplied with the expectation value of the local energy with respect to alpha. So this was the case with the harmonic oscillator, where we didn't need to think of the fact that the wave function is in general complex. So then the exercise, which I'm going to leave to you guys. So show this for the general case as well. So I'm taking the liberty of doing the simple case in the lectures, and I'm giving you the more difficult case as exercises. That's a standard trick when you teach. Show this for the general case of a standard wave function, where you now have a wave function which is complex. It's not so difficult to show that. It's basically you applying the same rules for derivatives, but taking into account that you also can use the hermeticity. And then when you use the hermeticity and take the derivatives of the wave functions, you will see that you get the same expression. Now, next challenge. You don't need to do this. That is to calculate the second derivative. So in this case, we have only one variable. So this is something which you would need if you now want to calculate the full Hessian matrix. And this is only for one variable. What you will end up then, if I did the counting correctly, is 7 integrals to evaluate. So now you understand why we don't want to calculate the second derivative. And typically the way this is done in the Monte Carlo calculations is either to use one of these gradient descent methods with different ways of approximating this parameter gamma, or to use quasi-Newton methods. But in principle, what we need to have now as a new programming element is to calculate this quantity and these two quantities here. And this is what I wanted to show you in the programs which we have online in the Jupyter Notebook. You can then see how we could set up the optimization path here with these new ingredients. So this will hopefully now give us the best possible parameters when we have a multidimensional object in terms of this parameter alpha. In our case, we have just one alpha. So by driving this dE alpha, so the ideal for us now is actually to have dE with respect to alpha, we want to have that one to 0. That's what we want. after a given number of iterations. So you see the basic philosophy, which we end up, so we need to calculate the gradients of the energy, and which in our case, since the expectation value of the energy is expressed as an integral, we end up with having to calculate some new integrals. And this is a technicality which we need to implement. So let me show you how this is done in the codes which we have online here. So let me just put this up again. So we are still taking this top-down approach. And in the lectures here, you will see the expressions which we end up having to set. In this specific case, I just took the derivative. This function here is actually a derivative, but you can rewrite this in a more compact form as the derivative of the logarithm. And this is, you will see from a technical point of view, is more convenient than this kind of brute force approach which I am implementing. However, the functions which I'm setting up are a little bit simpler. So you see now that, yeah, I have this as a challenge, find the corresponding expression for the variance. Now, if you look at the program here, this is now an implementation of this for this 2-electron case in 2 dimensions, where I have a trial wave function. And let me just go back to the Jupyter notebook. No, the whiteboard, sorry. So let me just do that. So in the example which you have in the slides, the trial wave function, example psi t in notebook, this is a case for 2 electrons in 2 dimensions. So this psi of t is now a function of R1 and R2. And then it has 2 parameters, alpha and beta. And the trial wave function is given as the harmonic oscillator case, 1/2 of alpha squared. This is 1 parameter. Then I have R1 squared plus R2 squared. So this is the harmonic oscillator part, the one body part of the wave function. This is what we call psi of one body. And then there is a correlation part which takes into account the divergence you have in kinetic energy when 2 particles are getting close. This is a 2-body kinetic energy, and the potential energy, which is now given by a Coulomb interaction when the 2 particles are getting close there. So you have a 1 over R1 minus R2 possible divergence. And this is given as a function of R12 divided by 1 plus beta R12, where R12 is now given by x1 minus x2 squared plus y1 minus y2 squared. So this is the function which you find in the lecture notes. Now for project number 1, when you look at these examples, you can just take away this one before we have included the interaction. So you can actually use these examples. That's the whole idea behind them. And you can just take it over and just take away the part which includes the correlated piece. So if we then go back to the Jupyter notebook and look at the way we have implemented it, you will now see the trial wave function here. This is the wave function. Then, in this specific case, I've calculated the local energy analytically by taking the derivatives of the wave function. And you get an uglier, slightly uglier expression. I have the derivative of the wave function, which is now given by these two parameters, alpha and beta. So this returns the derivative of the wave function ansat with respect to alpha and beta. So that means that when you look back at the expressions we have to code, I'm now calculating this quantity here. But I'm doing this in a more brute force way without the logarithm. So I'm just trying to stay with the equations here because this is something when it comes to neural networks, you may not have something which runs like a series of exponentials. So this is the derivative. So derivative 0 is the one with respect to alpha, and derivative 1 is the one with respect to beta. So this is just a compact way of encoding this one. Then I have the quantum force as before. And then I perform the energy minimization here. And I'm setting up the old position, everything as before. I have a loop of a Monte Carlo cycles. This is exactly what we've been discussing before. The Green's function, the metropolis sampling, etc. But now I'm adding these additional derivatives. And these additional derivatives, one is obviously the local energy. Then I have the derivative of psi. And then I have my delta psi, which now simply connects that one. And then I have the second derivative, which is the energy times the derivative of the wave function. So I'm setting up the three integrals into those two terms, which you see here. This term, this specific expectation value, and this two expectation values. And when I have that, I have calculated the derivatives, and then I return them. So the derivatives are now expectation values. So I need to update them after the number of Monte Carlo cycles, and then I divide by the number of Monte Carlo cycles, and then I have an expectation value. So this is my energy derivative. Okay? Then I'm setting up the number of particles. I have a guess for the initial parameters. I calculate the derivatives. I have two parameters. And then I perform a brute force number of iterations here. So I set up the alpha gradient and the beta gradient. These are the two derivatives. And then I simply perform a gradient descent, where I now have a learning rate, this parameter, which is now put to 10 to the minus 2. And this is my simple brute force gradient descent. And where I have coded, or rather hard-coded explicitly the expressions. So let's just run through it and see. This is going to take some time. So let's just do that one. And that should be running. So you will see that this is a pretty slow, and probably it may not finish in time. So what I've done after that, instead of using a plain gradient descent, as you see here, you can now see this is the energy I get. The exact value is 3. There is an error, so you will not get exactly 3. So there's a plus minus error. But you see now that my derivatives after 50 iterations are not exactly 0. So remember that you want to drive these derivatives to 0, right? So this is not the most efficient way of doing it, because if I now change this gamma here, that will give me another set of derivatives. So if I rerun it, then this is going to give me derivatives which may be worse or better, and you don't know that. So that becomes a parameter when you use this very, how to say, brute force approach. Then you have to tune this parameter, eta or gamma, as we called it, in front of the standard gradient descent. You see, in this case, it actually got better. In the previous case, we had 0.0 something. Now we actually have 10 to the minus 2 here. No, 2 times 10 to the minus 3. And here we have 5 times 10 to the minus 3. In the previous case, the error was, or the gradient was 10 to the minus 2. So this is a parameter you would need to tune, and you would typically need more iterations. But what you see now, if you're happy with this, if this defines your level of happiness, numerical happiness, then you have the optimal alpha and beta. If you note what we have here, we have used 10,000 iterations only. So instead of running 1 million, as we had in the cases before, for each value of alpha and beta, and I had 10 values for each. So I did this 100 times, 1 million times 100 times. I actually did 10,000 iterations. I should say that the exact value is 3. This is actually an amazing good result, an amazingly good result. These are the optimal parameters. And with that, I would then start my Monte Carlo machinery with these values here and perform the big calculation. Now I can do this in a smarter way. Since I have very few variables, the intensive part is the calculation of the integrals, but I can use Broyden's algorithm. And this is a quasi-Newton method, which allows us to make estimates of the second derivative. And we will discuss that in detail next week, together with other methods. Now, this method is included in the scientific Python in the optimization package. And here I have a function for the energy derivative, which is the same as the one you saw before. But now I'm also calculating the energy. So this algorithm wants a function for the energy, and it wants a function for the energy derivative. So the method is called Broyden, Farberg, and then I always forget the G and S. They are two more people who contributed to the algorithm. But this allows us to actually calculate the second derivative, and it needed only 9 iterations to actually get to a value which is close to 3 here as well. And these are the optimal parameters for the parameter alpha and beta. And then with those, you would then start the big calculation. So remember now that here we are starting with a random guess. Actually, now I started with this value. And the different methods will actually give you different optimal parameters. So look at these values here, 0.988 and 0.4. If you look at my plane gradient descent here, which you have up here, that gave me something which is close to, but not exactly the same value. So every time you run this, depending on your starting point, you will always get a slightly different result. So that means that what you need to do then is to run this several times and then take the average of the energies which you get. So every time you run this, you have to think of that as a numerical experiment. So I hope you see the overarching philosophy, and everything starts with a Taylor expansion. We truncate the Taylor expansion at the level of the second derivative. Then we obtain Newton-Raphson's method. We don't want to calculate the second derivative of the energy because that's going to give us way too many integrals to solve with their statistical uncertainty, because every integral we evaluate is evaluated statistically, which means that they have an error by themselves. So when we look back at the expressions we want to calculate for the derivatives, every quantity here carries a statistical value error, which we have neglected in these expressions. So if we were to calculate the second derivative, we would have even more integrals, which can then lead to further statistical errors. And we want to avoid that. So there's always this balance between calculating specific quantities contra the number of floating point operations we are willing to perform. Okay, this stops today's lecture.